welcome to the Breker tutorial on In-emulator UVM++ randomized test benches for high performance functional verification. Well, that's quite a mouthful. This tutorial is geared towards advanced UVM users who are A, working on complex IPs and or subsystems, B, who are thinking about how to optimize the use of emulation for their IP verification, and C, thinking about how to make their UVM environments available for use for firmware validation. My name is Adnan Hamid, and I am founder and CTO at Breker Verification System. In this tutorial, we will start by examining what UVM++ is and how we can use it to get efficient coverage closure in simulation. Then we can look at how we can use UVM++ to drive IP emulation platforms using simulation acceleration. Third, we'll look at how we can get firmware to run on UVM++ such that we can execute this firmware on the IP simulation and IP emulation. And finally, we will look at how we can reuse the UVM++ content for SoC system coherency verification. We have a large gap in our verification capabilities. As we go from IP verification at the UVM level to subsystems to full chip and finally to post-silicon, we have some very serious handoff steps. At the block level, we use UVM. At the SoC level, there's a great integration gap. We basically do ad hoc testing, and then the firmware for the system doesn't arrive or doesn't get tested till we get to system validation very late in the process. There are many problems with these flows. First, UVM is not scaling for us, especially as we get to complex IPs and subsystems. The test bench and the sequence development itself is becoming a beast, and that overshadows the actual verification work. As our IPs get more complex, simulation is simply not fast enough, and we have to have the emulation performance to get through the verification and the validation we want. However, UVM test benches and the sequences greatly slow down emulation, so that makes it non-viable. And we don't have very good test content to test our subsystems that involve multiple IPs. And finally, today's strategy of leaving firmware validation till silicon is available while working on System C models is weak. We really want them to be able to validate their firmware on our UVM environments, be it in simulation or emulation. The SoC guys have their own set of problems. They have a deep need to reuse the content we develop in UVM. They don't know how all the IPs work, and they need us to provide that information to them. And they need to integrate all our IP content together into multi-IP use cases and combine it with system coherency tests for topics such as cache coherency, power management, security, interrupts. The set of things that apply across all IPs goes on and on and on. Let's start by understanding what UVM++ is and how we might use it in simulation. UVM++ is simply a set of UVM-style APIs that interface to a PSS tool. They provide a procedural system Verilog style set of classes and are also implemented in C++ so that they can be used by firmware. This gives UVM experts an easy way to access the power of PSS tools without having to learn new language or new semantics. It also provides a seamless integration into existing UVM environments that can coexist with the current test bench, test cases, core boards, coverage, etc. So why do we need UVM++? Clearly, UVM is not scaling for us as our IPs become more complex and as we try to deal with multi-IP subsystems. We get our RTL from the designers. This is cool. We pull together the formal UVM environment with the interface VIPs, and this happens fairly efficiently. Then our real work is to go understand what our IPs and our subsystems want to do And this is the high value verification knowledge that we collect. But then we spend most of our time developing this thing called a UVM test bench involving control VIPs, complex scoreboards, sequences, virtual sequences, events, scheduling, memory management, whatever, and lock up all of this very valuable knowledge in a very, very complex implementation that nobody other than the original author can untangle. Now, whereas this gives that verification engineer a very good job security, it makes them immobile and they can't share this information easily with anybody else. So what do we propose to do? We propose to take that same high value knowledge, but capture it in a portable model using this so-called UVM++ library. Once we have that, from it, we will synthesize test cases. And these test cases will contain not only the stimulus, but the checks. They will be self-checking. They will generate coverage information, specifically scenario coverage information or stimulus coverage information, if you will. And they will generate high-level debug information, all from the synthesis flow. Then we will feed that into a so-called synthesizable verification OS that will synthesize that content down to whatever platform we're going to, be it a UVM IP bench, a subsystem bench, or a full chip SoC bench that's running actual software. How easy or hard is it for a UVM engineer to start using the UVM++ libraries? On the screen on the left, we have a shot of a tool called Track Designer, which I lovingly call PowerPoint for DV engineers. What we're capturing over here is use cases for AES crypto engine. The encrypt function takes two inputs, the clear text input and a key, and produces one output, the encrypted text. Similarly, the decrypt takes the encrypted text and a key and produces clear text output. We have set up utility functions that know how to write the input buffers and know how to check the output buffers. We can draw this picture and press a button, and the tool will generate for us the top-level stitch for this model. Or alternatively, if we choose, we can write this code by hand. All that is going on over here is reinstantiating the various actions that we showed and binding them together, connecting inputs to outputs, and finally saying that we're going to do one encrypt followed by one decrypt. This is all high-level connectivity. The real work is in explaining how an encryption process is actually done on the IP. This is the core verification knowledge that we figure out as UVM engineers. To define this information, we declare a class called AES encrypt, and action is simply works just like a system Verilog class. In there, we define inputs for a clear text and a key, and an output, which is going to be encrypted text. And we lock a resource. This lock tells the UVM++ library that only one thread can use this piece of IP at a time. Then we constrain our data length. Inputs, the key, and the output are all going to be 16 bytes long, and we get a handle on our register block. In the post-solve function, we are simply telling our producers and our consumers what addresses they should write to in the case of inputs and what addresses they should read from in the case of outputs. Then in the main body of this action, we first kick off the crypto operation by setting the start bit, setting the mode to 0 for encrypt, and writing that register. Then we poll until the done bit in this control register is set to 1. And then finally, we predict the expected output by calling a reference model and forwarding that expected output to our consumer, namely this check function. Anybody who's a UVM author will quickly recognize that the register APIs look just like what the UVM RAL registers look like, and overall, writing the sequence looks very much like writing a UVM sequence. Fair enough, you say. I can imagine writing that model, but how do I tie that into my existing test bench? So let's say we had a UVM unit bench for a little AES block, and its registers were written and read via an APB VIP. And imagine this is a working UVM test bench. You already have some sequences running on it. Maybe you already have a scoreboard within it, and so on. We will take this environment and we will link in a DPI library provided by the tool. We will compile in some UVM code generated by the tool and pass it a pointer to the generated test case. If we don't pass this, all of the other content is completely idle and your environment runs as normal. If we do pass in one of these TBX files, then what we do is we invoke on the APB VIP a sequence. The sequence works exactly how you like your sequences to work in your UVM environment. But the body of that UVM sequence is getting requests from the tool and sending responses back to the tool. And the code you see in bold over here is what was generated into this generated system Verilog code. So net, it provides a very lightweight integration to drive your existing VIPs, your existing interface VIPs, that in a way that bypasses the rest of your environment when running one of a UVM++ test, while leaving the rest of your environment unchanged for running the remaining tests. When we run the test, we get a nice debug view. This is a picture of a tool called Correct Debug that lets us see the test that has run. We see that we're doing a write to set up the input clear text. We're doing a write to set up the key. We're calling the crypto function, and then we're checking the results. Then we're doing a write to send encrypted text, another key, and then decrypting and checking the decrypt. On the encrypt function, we can see what register writes we're going to be passing to that APB interface. We can see the poll that we will do on the APB interface. And as the test runs, you can see how time is progressing as we write these registers, wait for the poll, and then eventually the check carries on, and presumably it passed because the block is green. Now let's look at composing together multiple UVM++ IP models. We are back in Track Designers. We are back to our crypto block. But now, instead of having a crypto block only being driven by our utility buffer write operation, we will provide the ability to drive it from a DMA transfer as well. So DMA will allocate, this memory source object will allocate some memory. The DMA will copy the memory into the AES buffers and so on. Again, we can draw this picture and the tool will generate the framework code for us, or we can write this by hand. But the important part is, how do we actually model that DMA transfer? Again, we define a new action. We talk about its inputs and its outputs, which are the data buffers, and we lock a DMA resource, a DMA channel that we're going to work on. A DMA causes its input length and its output length must be the same, so we constrain that accordingly. And we get a handle on a set of registers. And then the body of this action, we are simply setting the source and destination addresses in the DMA. We are marking both the source and the destination for address increments, so addresses are marching along. We start the transfer by defining the size and setting the start bit. We poll till the register declares that the transfer is complete. And then we forward our input expect data that was set up by this mem source function to the output expect, such that the crypto block can use whatever data we're sending it for its prediction. So the point is that we can easily define models for each of these IPs and stitch them together in these flowcharts and let the tool go connect these IPs together and generate test cases. But wait, you say. You showed me how to connect UVM++ to my IP test bench. How does it connect to my subsystem test bench? Well, unsurprisingly, using a very similar mechanism. Again, we will link in the DPI and some UVM code generated by the tool and pass it a link to the generated test case. And again, we will create sequences that connect to each of your interface VIPs. But in this case, we're probably talking to something like an AXI or a CHI VIP as opposed to an APB VIP. And that VIP comes to the fabric to talk to the various IPs. Again, we are getting requests from the tool, sending responses back to the tool. We can run the test case, and now we get a schedule with different operations happening in each of our two CPU VIPs, our two AXI VIPs. We see over here a DMA transfer to set a input clear text, DMA transfer to set up the key, and then we do a decrypt, and then we do a check, and so on. We can click on the DMA operations. We can see the register writes he will send into the interface VIPs for AXI, and we see the test executing. Using UVM++ with our UVM environments give us a number of advantages that come from the PSS tools. One of them is 3D coverage. What is 3D coverage? We're going to talk about combinatorial coverage, sequential coverage, and concurrency coverage. Combinatorial coverage is similar to what we get in System Verilog. It is asking, has each of the functions been tested? And we'll figure this out by understanding whether we've walked through each of the actions that we've defined for the tool. Next, we'll talk about sequential coverage. The tool can think about all the possible paths through the set of flows that we've defined and tell us which of those paths are reachable and which of those reachable paths have been covered. We can furthermore go in and constrain exactly which paths we want covered and focus the test generation to that subset of paths. And third, the tool will talk about concurrency coverage. As the test runs, the tool is keeping track of when different operations began and finished, and the tool can tell us how often we've seen overlap between these operations, and this information can also be used for doing temporal analysis for performance, such as throughput analysis and latency analysis. Another advantage we get with UVM++ in a UVM environment is the availability of high-level scenario debug. So this is another view of our Trek debug tool, and in this case, we are seeing a test that is driving 4 CPU interfaces, 4 XI interfaces, with only 1 thread per interface. The tool can put multiple threads on each interface if we ask it to. This picture updates dynamically as the test is running. The green nodes have finished running, the yellow nodes are running, the blue nodes are waiting to run, the red nodes have failed. When a node fails, you can click on it, and all the other arrows go away, and you can see what is the producer that provided input to that particular action. The tool gives us an overview of what is the memory usage by this test. We see here we have 3 regions set up, DDR0, DDR1, and RT, and the shading in those regions tell us what addresses have been used. The darker the shading, the more times we have hit those addresses. The tool predicts for us for each action, not only what addresses will be used by that action, but also what will be the value in memory before that action runs and what will be the value in memory after the action runs. This is all predicted before the test runs, and of course is very useful for debug when something goes wrong. You can click on any of these nodes and the tool will show you either what transactions we're going to send if we're talking to an interface VIP, or what C code we're going to run if we're running on a CPU. And finally, you get the simulator's execution log reflected into this window, at least the messages that pertain to what this test is doing. And then finally, this high-level debug is integrated down with the waveform viewers such as Verdi, such that when you find a failure over here, you can click on the failing time over here, where Verdi's cursor will go to that point in time. You can debug in Verdi and say, okay, my real problem is 2,000 clocks back. When we move the cursor there, the tool's cursor will show us what we're driving at that point in time. UVM++ can be used in one of 3 possible modes. Pre-generated constructs mean that we've decided at generation time exactly what is going to happen in the test. Reactive means we decide what to do next based on what we just saw from the test bench. This is what UVM users are used to seeing. And hybrid means we're going to do some things in pre-generation constructs and some things with reactive constructs. In general, we should prefer to use pre-generation constructs where possible. This gives us better performance in IP emulation and simulation acceleration. It's easier to reuse an SoC and post-silicon. And most of the reactive things that we're used to doing in UVM, such as checking results, polling for operation to finish, waiting for an interrupt, scheduling in a way such that one task doesn't start until another task is finished, all these are very much handled by the synthesizable verification OS. We should use fully reactive constructs for block level verification, where the next step we take in the test is very much a function of exactly what we saw from the device under test, and its behaviors cannot really be predicted. In hybrid mode, what we're able to do is move most of the work to pre-generation, where we are efficient and do reactively what is necessary. This means we take a small sacrifice in simplicity and in performance, but it does give us the flexibility to be reactive where we must be reactive. To bring this all together, the synthesizable verification OS provides an isolation layer. Under the layer, it talks to your existing UVM test bench where everything remains the same, and we can continue to use our existing scoreboards, existing test cases, use RAL, and so on. Above this isolation layer, we use UVM++ based scenarios that can be generated and applied down to our environment. And that in turn allows that UVM++ content to be ported to other platforms as the design scales. So looking at this picture from the same model, we can generate test cases for either IPs or SoCs, and we'll see how we can move them from unit benches to subsystem benches. We just saw examples of that in the prior slides, and in the future slides we'll see how we'll move this to IP emulation and subsystem emulation. Now let's look at how we can reuse content developed with UVM++ to provide performant IP emulation. As our IPs get more complex, simulation is getting way too slow, and we are spending hours and hours and hours waiting for each simulation to run. However, getting tests to run on emulation test benches that do simulation acceleration for IPs is hard. First, we simply don't have enough content to run on these emulators, especially if you're talking about multi-IP subsystems, right? So not only my crypto block, but my crypto block, my DMA block, and my UART block all working together in a headless environment. Second, emulation compiles are ridiculously long. We already hurt in simulation when the blocks are big, because every time we change and create some new UVM content, new UVM sequence, a test bench change, we have to go through a long compile flow. In emulation, this is 10 times worse. The killer thing in simulation acceleration is when we try to reuse our UVM environments with the emulator, the UVM solve and the simulation greatly slows down what the box can do, making reuse almost unviable, right? We typically tend not to use emulators for IP verification because of this problem, or if we do, we are doing some very special jury rigging for the emulation environment. And finally, trying to collect all the coverage data and debug data that we need to figure out what went wrong in failing tests also slows down our emulator.
Okay.
So can we find ways of solving all these problems that make it work efficiently? We know the emulators are already out there. We know that there's time available in the emulators. Simply finding a way to use them efficiently with our verification content at the IP level is what the big problem is. So how do we solve this with UVM++ libraries? Well, first, we're doing all the randomization offline. We solve the entire schedule and all the operations we're going to do before the test runs. So this means the solve time doesn't affect the emulation runtime. Second, we are actually generating all our coverage upfront, and in fact generating a suite of test cases to target a certain coverage objective, so we can know a priori whether these tests are worth running. Third, each generated test is loaded straight into the host memory, and we don't have to recompile the emulation environment from test to test, so this makes it much more efficient. And finally, the way the high-level debug works, very little information must be saved from the actual runtime, so we don't have to slow down the emulator. Let's look at some of this in detail. First, how do we tie UVM++ into now an IP emulation environment for simulation acceleration? Well, the environment looks very similar to what we've been looking at before, but now it's sitting inside a box. Again, we will link in our shared object and give it a pointer to our test case. But now we're going to drive the emulator's accelerated VIPs. And depending on whose emulator you're using and how the environment works, this thing changes from environment to environment. But generally, these platforms like to have their transactors driven from a C++ API. And now you're seeing a sequence very similar to what we saw in UVM, but now done in C++, where we are pulling requests from this test case, driving them into the accelerated transactor, getting the responses back and sending them back to the tool for checking. Why is this fast? Well, first, all the randomization is done up front. Before we ever started the emulator, the tool walked through the model and generated this TBX file that contains the entire schedule of operations with all the randomization that was done offline. And we can serve transactions from that test case very, very quickly. Second, because that test file is loaded by the runtime component, this checkbox, it's to be loaded directly into the tool's, into the host's memory. We don't need to recompile on the emulator from test to test. Of course, this also helps us when we're doing simulation, because simulation compiles can also be long. Instead of trying to capture coverage data as the emulator is running, which slows down the emulator, the coverage reachability and coverage analysis is actually available right after we generate the tests, even before we run anything. This means we can review the coverage achieved by a suite of tests before even deciding whether it should be committed to emulation. And by not needing to track coverage from the emulator, we can greatly speed up its execution. The idea over here is we've already looked at RTL coverage and simulation. We have some belief that our models are hitting what they need to model, what they need to hit, and now we can run at speed on emulation. Finally, let's talk about capturing debug data. We're dealing with complex IPs and/or complex subsystems. Things are going to go wrong. When they go wrong, we have to be able to debug what's going on. Unfortunately, capturing detailed debug information from the emulator via FSDB, while possible, slows everything down. The good news is that the synthesizable verification OS only needs to collect minimal debug data at runtime. This is true because most of the debug information for the test case is already available and built into the generated schedule. This means we can greatly reduce the amount of debug information the emulator must create and allows us to debug our failures quickly. Usually we can figure out what's going wrong straight from the high-level debug. If we can't, only then must we go rerun the test case in emulation with FSDB enabled so we can get our low-level waveforms, or take the test case back to simulation and run it over there. In summary, the synthesizable verification OS layer allows the UVM++ content developed in simulation to be ported to emulation/simulation acceleration. The way UVM++ works, it allows emulation to run in a very high-performance manner and allows us to use those boxes to its best advantage for IP verification. Now let's look at how we can leverage the UVM++ capabilities to allow firmware to run on our IP simulation and IP emulation platforms. We all know as UVM engineers that a bunch of software yahoos out there trying to develop low-level IP firmware that is supposed to run on our blocks, and they systematically screw up how they should use our IPs, and they keep coming and asking us lots of difficult questions and putting us into difficult debug that we just don't want to do. And meanwhile, sorry firmware guys, but these hardware guys do you no favors. They give you absolutely no way of figuring out exactly how their IP should work. So let's see if we can do something better for all of us. We know we have routines for each of our IPs, but how are we to run that firmware if there is no CPU in the system? How can we provide all the support services this IP needs, such as memory management, interrupt handling, scheduling? And how do we load and run that firmware in a way that can run in our simulation environments? So the secret over here is to implement the firmware HAL, or hardware abstraction layer, in terms of UVM++ APIs. Now note, early in this presentation, we talked about the fact that the UVM++ APIs are also available in C, C++. When you look at these firmware routines, and over here I've provided a very, very simplistic example to make the point, we will find routines that actually do operations with our IPs are built in terms of low-level macros, typically called a HAL, or a hardware abstraction layer. For example, register write will know the offset of a particular IP instance, the offset of the register within that instance, and then what value to write to it. The idea over here is we can implement those HAL macros in terms of UVM++ APIs, and now we're using the CC++ variant of these APIs. And that in turn comes right back to the synthesizable verification OS. And now this, we can run the firmware routines on top of the synthesizable verification OS and have it drive either our simulation environment or our UVM environment. The upshot of all of this is that the synthesizable verification OS layer gives us enough OS-like capabilities to allow us to run this firmware without having to boot a complete Linux environment. The firmware guys talk to the registers via headers generated into their software. Those get all mapped into our UVM RAL registers, eventually in our UVM environments. Memory allocation, I/O transactions are all managed by the synthesizable verification OS. And other OS operations such as scheduling and synchronization are all also handled by the synthesizable verification OS. In fact, the synthesizable verification OS is a general purpose tool where on the north side of it, on the top side of it, we have the UVM++ APIs, and the south side of it, we are synthesizing down to various platforms what they need to satisfy what those UVM++ calls need to do. So one thing it does for us is all our scheduling. This involves both path scheduling, deciding what operation will run after what operation on which thread, where maybe each of these threads is driving a different CHI or AXI IP in our system. It is scheduling memory and doing memory scheduling in a way to create lots of system stress. And once we have these APIs, the APIs can be made portable from virtual models down to UVM simulation to subsystem to full chip. We've talked about that today. And make it reusable from simulation to emulation to hardware prototyping all the way to post-silicon. In this presentation, we're only talking about simulation and emulation. And then finally, the tool also automates the synchronization between what's happening on the embedded side with what's happening on the I/O side. For example, if you're dealing with a PCI Express test, you might need to synchronize what is happening on the CPUs with what is happening on the upstream PCI traffic to create interesting coherency scenarios. So in summary, this gives us a flow where we can take our firmware routines and apply them at block level UVM simulation for individual IPs, combine those firmware routines, run them in subsystem simulation using multi-IP scenarios, also probably coming off of the UVM++ graph-based models. Then we can port that content to either IP emulation or subsystem emulation. And then, by the way, what we are not covering in this tutorial is the same content can be taken to full chip SoC, where now the firmware is actually running on the embedded CPUs. Finally, let's talk about the interests of the SoC integration team, okay? The folks who are the consumers of our IPs that we're doing IP verification with. The system guys very, very much care about being able to reuse the content we're building in IP verification, right? We are the only ones who know really what the IPs are doing, and they want to be able to reuse this. Not only do they want to reuse it, they want to reuse them to create multi-IP scenarios, just like we talked about how we can compose multi-IP UVM++ models to run on a headless subsystem environment. They want to run in a full system environment. And then they want to cross that with a bunch of system coherency tests. Think of things like cache coherency, power management, security, interrupt management, and the list goes on and on and on. And there are libraries available for a lot of these system coherency tests, and they can combine those libraries with the UVM++ models we give them to achieve a very good system level verification. And this can be done both in SoC simulation as well as SoC emulation, and can also be ported to FPGA prototypes and post-silicon. Each of these apps can be configured and expanded as needed for each system, so they have flexibility at the Trek app level themselves. And in summary, we can combine the Trek apps provided by Breker and Trek apps built by the system teams with the UVM++ models that we're building for in IP verification to create a full flow where they can go from UVM to subsystem to full chip, go from simulation to emulation to post-silicon. In summary, in this tutorial today, we have looked at what UVM++ is. All it is a library of UVM-like APIs as an interface into a PSS tool. We looked at how that can be used in simulation to both build models for individual IPs and to compose multiple IP models into a subsystem use case. We looked at how UVM++ can drive emulation in a very efficient manner. We looked at how we can bring the firmware guys to our IP simulation and subsystem simulation environments by having the firmware implemented on top of the C++ variant of the UVM++ APIs. And finally, we talked about how all of this content can then be reused by the SoC integration teams. Thank you for your attention, and now I'm available for any questions. So, let's see, am I on video? Hello, everybody. We are now open for questions. There are a bunch of them in the chat. And please, if you raise your hands, we can do these questions live as well. Can somebody confirm that you can hear my voice?
Hi, Adnan, it's Dave here. Yes, so we can hear you and see you.
Okay.
And maybe if you like, I can sort of work through some of these questions in the chat so we can go from there.
Sounds very good.
So people like the idea of system UVM. Do you just want to quickly mention what system UVM is versus UVM++ and what on earth that is all about?
Yes. So this video was recorded about 2 months ago. And since then, we renamed it to system UVM. And this was announced this morning. And the idea is this, right, that we're hopefully many of us on this meeting are UVM engineers. I walk the halls, many UVM engineers, these days the virtual halls. And as UVM engineers, we're really the only ones that figure out how IPs work, right? Nobody else in the company knows how the thing works as well as we do. But the trouble is we lock up all that information in our UVM environment. And system UVM just lets us put it in a format that we can take advantages of the synthesis capabilities that these PSS tools bring us while using languages we're familiar with. And it effectively forms an isolation layer between our complex UVM environments. Let's not pretend, right? Bringing up a UVM environment that keeps our little IP, little or big IP, alive, tracking it, resetting it is complicated. So we still have to do all of that, but the actual content can come from system UVM and now can be used by people upstream, hopefully reducing how much they pull on us to go and debug all the cases they screw up, right? Be it in integration or post-silicon. Okay. So that's system UVM, Dave. Where should we go from there?
Yeah, so Robert was pretty prolific on this on the chat. Thank you, Robert.
Yeah.
And he has a question here. So with system UVM, is the action body a replacement for the previous action exec body, SV, etc.?
So Robert, sharp eyes. Short answer, yes, but I'd like to give a little bit of a longer answer, right? PSS is an awesome declarative language, right? And it's very, very powerful. The trouble we're finding is that it is a different programming semantic than most of us are used to. And what we're doing with system UVM is making the language semantically operate like you're used to in system Verilog with classes and persistent objects and so on, right? So yes, the motivation to rename the exec body to a void body is simply to remind us that now we're operating as regular class member functions and not with declarative nature of what PSS brings us.
Right. Okay, and then Robert also mentions that I think you had a chat here, Robert, right, where you said it'd be good to see more UVM-like constructs within the PSS constructs, and that is precisely what we try to do here with System UVM. You know, I think it's fair to say we've seen this at several DVCons where people stood up at panels and things and said, you know, why is it we're putting this whole big new language together when we should just be doing all this stuff in something like System Verilog and UVM? So there are definitely good reasons why PSS exists and what it's trying to do. But I think like UVM was able to sort of contain and frame System Verilog, we can do the same thing with PSS, and that's what we've basically done to provide these kind of UVM-like constructs. So yes, that's a great observation, Robert. Right. Anything you would add, Adnan?
And putting specifics to that, right? I think UVM has done registers reasonably well. UVM has done TLMs very well. And we are simply re-implementing those use models in PSS, in System UVM, which is a wrapper for PSS. I think the memory scheduling schemes in PSS are better, so that's in System UVM. The scheduling is better in PSS, and that's also in System UVM. The resource management is better in PSS, and that's also in System UVM. So we're trying to make it available in a very familiar format, but bring the strengths of the new technologies.
Yeah. And then Robert also goes on to actually a very interesting question, considering the pre-gen PSS constructs versus the fully reactive constructs and how we need to balance of those. And I know you have a good answer for this.
So where is Robert? Will Robert talk to me? That is actually
yeah, Robert, do you want to say on the slide? Feel free.
Hi guys, very interesting
talk.
Can you hear me?
Okay. Yes, we can, Robert. Yeah.
Okay. So yes, I was very interested, especially with the three modes. Thank you for summarizing those. We've seen a lot of traffic with the pre-gen PSS and DSL style test output, and obviously there's great value in that. But sometimes what happens is, depending on what the RTL is doing, we want to capture some data and send it backwards, as we normally would inside a simulation UVM environment, to kind of react to what the RTL is doing and then make decisions based on what the RTL output was. So now with pre-gen, everything is kind of predetermined upfront. So I'm curious to know how the reactive side of PSS can be achieved, and also what the status is with respect to the language versus tools.
Yes. So I think the answer to the last question is straightforward, right? There is no System UVM is absolutely built to be reactive or pre-gen, right? Or hybrid. This is what it says. So what's the real issue? Right? If you're talking about something like, I'm going to take extremes, right? If you're talking about something like a DMA engine, where you're going to do some register programs to make something happen, pre-gen will probably work fine in UVM, and this makes the vertical reuse to the system super easy. You go way to the other extreme, you get into some certain subcomponents of an IP, and there are responses that the hardware is providing that directly drive what is the next thing you can do. So an example might be, say, some kind of resource allocator. It gives you back, you ask for something, it gives you back a tag, and you've got to use that later on. There is no way you can pre-gen that, right? So you've got to go either full reactive or this hybrid reactive. And my observation on this, Robert, is that the lower we get into the implementation, the more the need for reactiveness, right? The higher up we are, clearly a CPU can't be reactive to something hardware is doing, and most of the designs eventually go into itself. Or consider things like networking, right? There are certain things that the hardware will issue in terms of sources, source IP, source and sequence numbers that you have to be reactive to. So in the end, my conclusion, I think, is that we try to be pre-gen where we can because it's easier to reuse. We go full reactive when we have to. And in between, the hybrid idea is to say, hey, I'm going to pre-gen something, but I'm going to say at this point, I'm expecting some sort of a response from the DUT, and we tag it and then say, okay, now give back the DUT whatever value it told you with this tag. So this is the idea behind pre-gen reactive versus hybrid.
Right.
May I quickly ask a quick follow-up?
Yes, please. So this is a deep question. It's not a simple thing to answer. Huh?
Yeah. So from the reactive side of things, how would what would that look like in the form of PSS code to accept this type of reactive feedback from the RTL? Like, is there an equivalent, like a reverse action that gives you, or like a buffer variable that you get it in?
So in system UVM, if you want to drive a TLM into a VIP, you would create a TLM port and put the request. If you're waiting for a response from the DUT, you would create a TLM port and get a transaction. So it would look just like it does in UVM. Okay.
And this would be an action or like a shared, I forget what they're calling it now, but like a buffer variable that would store these entries that were got from TLM FIFOs from the RTL to make this future decisions. Like an action could say, yes, whatever, TLM port get, and then make your decision and then write out to another port, or at least write out to the port that the original transaction was sent out on.
Exactly. In system UVM, lifetimes of variables are the same as you used to in UVM and system Verilog, right? So you could have a local transaction that you get from one port to do some math on and send to another port, or you could store it in some kind of queue or something and then later use it in some other action. So the point over here, Robert, is to make it completely familiar and make all those questions go away.
And finally, once you get this reactive feedback back, future generations, which be in the pre-gen are, just generated at, I guess, at build time, will future transactions, I guess, at runtime now, be reflective or take into account either constraints or feedback, metadata from the RTL?
This is the point behind reactive generation, right? The main thing about reactive generation, the main necessity of it, is to be able to influence later solves using responses from the DUT.
And is there a way to kind of blend the pre-generated traffic, which would kind of can be melded with, I guess, reactive future ones? So for example, if I were to randomize 1 through 10 using pre-gen, but based on some input, I can't use 1 through, I guess 7 through 10 anymore. And so now I need to generate new stimulus, let's say 11 through 15, right? And so now my test cases, which originally started off at 10, now have to be, I guess, 7 pre-gen. Then because you got some feedback, you now need to randomize and create more stimulus, let's say 11 through 15. So would the tools, would that be the flow? Or would it just be transactions within the same test?
Pretty much, right? So the idea behind, so you're basically spelling out the hybrid model. And the idea behind the hybrid model is at pre-gen time, you generate operations that invoke reactive actions. So that allows you to go do some reactive thing and then come back and you could carry on with your pre-gen sequence. Yeah. But great question.
Thank you so much.
Yeah, thank you, Robert. Okay, Adnan, so Subramoni here has a couple of questions, which I think is one big question, leading on from the reactive constructs. So he says, isn't the coverage achieved dependent on the specific action chosen at runtime? And then goes on to say, if that is the case, how do we compute coverage before we run the test?
This is very, very true, right? So Breker is using these AI planning algorithms to traverse these models, right, whether it's system UVM or PSS. And planning algorithms really want to turn this in and turn the entire graph of actions into a search problem, right? It's just basically statistical search as opposed to random solve. And the searches can easily be tuned to have policies that go to coverage closure. Now, this works whether you're pre-genning or you're doing reactive test generation, right? The search algorithm can happily search through its graph and stop at each action and drive something into a TLM port or whatever. The issue at the point where it becomes difficult to close coverage, even for a planning algorithm, when let's say you get to a particular action and you have two choices for your next step, and that choice is dependent on something coming back from the DUT, right? If the DUT gives you a 1, you're going to action A. If the DUT gives you a 0, you're going to go to action B. If the DUT never gives us an A and gives us a 1, the planning algorithm can never go to action A. So yes, you can't close coverage over there, and that'll be clearly apparent when you look at the sequential coverage that we were unable to close that. So yes, these problems very much exist.
Yeah, and actually Subramoni has, right at the end of the chat, has another question here, which is, I think, a really important one. So I'm going to just dive straight into it and then go back. And what he says is, long-term, do you see system UVM, UVM++, replacing UVM as the main vehicle for IP verification or as a supplement? And the reason I want to bring this up is, and a very, very important point that we need to bring out here, is all this system UVM stuff is very much built on top of regular UVM. So you know, we recognize that UVM is widely used. It's a very robust and strong standard and very powerful. And what we're trying to do is augment it. We're not trying to find a replacement. And that's a really, really important point, I think. And now I'll let Adnan make it again.
Yes, exactly. I mean, the same point. I'll say exactly the same thing again. Yes, I think UVM is great. First, UVM is not going away, right? System UVM is layered on top of UVM. I think UVM is great to set up an environment to get all your interface UVCs, VIPs hooked up. And then where we get lost is building our scoreboards and our control UVCs and our sequences and all of this that takes a lot of time. And system UVM is very much architected to drive the interface VIPs directly.
Yes. So Suresh has a question, back to the coverage question. If coverage data from emulation is not collected, how are we ensuring RTL coverage is as expected?
Yeah, I think this is an important question. So we definitely, whether we're using system Verilog, system UVM or PSS, we definitely need RTL coverage, right? Whether we're doing code coverage, branch coverage, or cover points, whatever. Presumably, we're going to run some quantity of these tests in simulation, and we can get coverage over there. And you're going to need to, and this is a must, right? I think the RTL coverage will give us a combinatorial coverage, and then we can rely on system UVM to give us a sequential coverage and a temporal coverage. Now, the decision on whether you want to take the cost of tracking RTL coverage in emulation is, I think, a little bit yours to make, right? There's a cost to it. It slows down the box. There's a benefit to it, which is you can measure the coverage. In the ideal world, we are seeing at least each piece of RTL coverage done in simulation. And perhaps we are dedicating, I mean, for the first time, we get to take this UVM content and move it to emulation, right? Emulation doesn't do well with UVM test benches because the solving slows everything down. If you can get the UVM content in a pre-gen scheme, you can run it very efficiently in emulation. And perhaps we're letting emulation run all the cross combinations, having confirmed for ourselves that RTL coverage was satisfied in simulation. So this is a little bit of decision on the user side.
Okay, so here's another key pertinent question from Roshi here. Will system UVM be donated to the PSS 2.1 standard, including the synthesizable feature? Do you want to take it, or shall I add on?
Oh, I think, Dave, this is a question for you.
Okay. Well, so yeah, so it's a great question. And here's our thought, right? And this is, of course, evolving as time goes on. So this idea of system UVM, Breker's had around for actually quite a while, a few years, and we've been developing it with a bunch of customers of ours who wanted to see some of the same UVM constructs or UVM sort of classes layered on top of PSS. So it's been working really well. We realized, I don't know, quite a few months ago now that we needed to sort of bring all this together and create some kind of initially proprietary kind of mechanism so that, so that people could try out this kind of standards approach before we actually donated it somewhere. But I do believe the plan should be that it's going to get donated to someone, and the PSS committee would be the obvious place, of course, or maybe the UVM committee. I'm not exactly sure. I think what we need to do is evolve it first with any company that's interested in looking at it and trying to use it, and sort of building it into a place where it can be donated and standardized in a very practical kind of fashion. So that's our basic aim, is to do that. But we want to make sure it's as robust as it can be first. Would you agree with that, Adnan?
Wholeheartedly.
Yeah.
Absolutely.
Yeah. One other thing I would add as well is, of course, this is just a class library based on standard PSS. So today, because it's based on standard PSS, it should work with other PSS tools. And that's how we've tried to design it. Cool. Okay. Let's see. Subramoni has a couple more.
We got 5 minutes left. Yeah. So
okay.
Yes.
Yeah.
Mm-hmm.
Okay, actually, that was one of Subramoni's comments. And then, given that this is a supplement, isn't there a cost of redeveloping the sequences for IP verification in both UVM and in system UVM?
So this, I think, is a key question, right? And the answer is that would never, ever make sense, right? We should not do that. If you already have your sequences in UVM, we should use them. We should call them from system UVM, right? So it's easy to do. The point over here is that for larger IPs, UVM is simply not scaling up, right? When you need lots of concurrency, lots of complex sequences, people are not able to create all the test cases they want. Building scoreboards gets really hard. And system UVM very much wants to generate self-checking test cases, right? So self-checking sequences and doing them concurrently. So the idea very much is you build your base UVM environment with the interface UVCs, otherwise known as VIPs, and then use system UVM to define the actual scenarios. And those can run in addition to any legacy sequences you already have. So certainly we are not trying to do things twice. And certainly we are working on top of UVM. And certainly, I hope you got this from the presentation, that the integration scheme is carefully designed so that everything in your existing UVM environment continues to work the way it worked before. You don't have to do an A or B choice.
Mm-hmm. If you don't mind, maybe can I ask kind of a clarifying question? So, is it the case that the sequences that are there in UVM would be called by kind of the description in system UVM, right? If we have like some kind of path that we define in system UVM, the sequences themselves would just be leveraged to achieve the path?
They can be, yes. So imagine that the system UVM goes through a series of actions, and each of those actions are invoking pre-existing native UVM sequences.
Thank you.
Yeah, excellent.
Which brings us to Mike's question.
Indeed. Oh, there we go. Okay, Mike, go ahead. Yes. Go ahead, Adnan.
Yes. So Mike Baird, you want to vocalize the question, or you want me to read it off the chat?
Yeah, I could vocalize the question. I mean, when you do use a sequence that's UVM, I mean, how do you get that to your embedded C environment then?
You cannot easily, right? So these are, again, the trade-offs. They are, on the one hand, if you're sitting on a UVM environment that has, a few hundred sequences built, you don't want to throw them away, and maybe you want to take advantage of them. But if you're looking for the reuse, that reuse won't come until you re-implement the sequence in system UVM. So these are trade-offs to be made on a per project basis. Yes.
So no magic there that you had, right?
No magic. Sorry, sir.
Okay, thanks.
Hey, thank you, Mike. So we're out of time. I'm surprised no one asked us for Adnan to give us a tune, but I guess he's not going to do that today, right, Adnan? Okay, thank you very much, everyone. So once again, if you are interested in more information on this system UVM idea, there is a page on our website, brekersystems.com/systemuvm. which has a load of demos and this, that, and the other on it. And with that, I'd like to thank Adnan and thank you all for attending. Very interesting session. Really appreciate giving up an hour of your time for this. Thank you.
Thank you, everybody, for coming.
Can you please share the link to the website where we can see the demos?
Yes, sorry. So brekersystems.com/systemuvm, and there's a demo on it. I will say this: we had some sound quality problems with the demo, so we're redoing it right now. So if you give it a couple of hours, you'll get a much better quality audio-wise demo.
Okay, thank you.
Okay, great. Thank you, Nitin.